Hi, and welcome to the lecture on statistical linear regression models as part of the Regression Modeling Coursera course, which is part of our data science specialization. My name is Brian Caffo, and I'm a professor in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. The class is co-taught by my co-instructors and colleagues Jeff Leake and Roger Pang. Finding a good regression line using least squares is really simply a mathematical procedure. However, we'd like to do statistics. We'd like to draw inferences based on our data. In other words, we'd like to generalize from our data to a population using statistical models, and that's what we're going to talk about in the statistical linear regression lecture today. So let's consider our probabilistic model for linear regression, and we're going to start with one of the most simple ones. Our response yi is our line beta naught plus beta 1 xi, where we don't know beta naught or beta 1. These are the population parameters that we would like to estimate. Xi is a collection of explanatory variables that we do know. And then to make it a statistical model, we're going to add IID Gaussian errors, which I'm going to denote epsilon I. So the epsilon i's are going to be assumed to be normal mu sigma squared. There's a lot of different ways to interpret these independent errors. Perhaps one of the easier ones is to think they're the accumulation of a lot of variables that you didn't model but maybe should have, that act together on the response in a way that can be modeled as if independent and identically distributed Gaussian errors. However, let's put these kind of difficult interpretation issues aside for the time being and simply talk about how we mechanically work with statistical inference for regression. I would note that the expected value of the response given a particular value of the regressor is simply the line at that regressor, beta naught plus beta 1 xi. And the variance of the response at any particular value of the regressor is sigma squared. This latter point, let me elaborate just a little bit. This is the variance around the regression line. This is not the variance of the response. So it will be lower than the variance of the response by itself because you've explained away some of the variation with x by conditioning on x. I would also note that both this expected value and the variance are population quantities. They have sample analogs that we'll estimate, but right now these are population quantities. These are the estimands that we would really like to know. Now that we have a formal statistical framework, we can interpret our regression coefficients with respect to that framework. Take, for example, the intercept. It's the expected value of y given that the regressor is 0. And here I'm simply plugging into the formula. Note that the regressor being equal to 0 is often not of interest in the study. For example, if the regression variable is blood pressure, probably you're not interested in the response among people with blood pressure of 0. However, there's an easy fix for this. Consider just shifting our regression variable by a constant a. And here in this equation, I've just subtracted off an a here, which means I have to add an a beta 1 over here to have done nothing, to have simply added 0. Well, this is exactly rewriting the regression equation as beta naught tilde plus beta 1 times x minus a new regression line with a new intercept, the same slope, and my regressor now shifted by a constant a. So this goes to show you that if you shift your regressor by a constant, it doesn't change the slope, however it does change the intercept. Now the intercept is interpreted not when x is 0, but when x is this value that you shifted it by, a. A very common constant to do is the average, set a equal to the average of the x variable. Then your intercept would be interpreted as the expected value of the response when the regressor is at the average value of the x's. Let's see if we can figure out a model-based interpretation of our regression coefficient. Now it's a slope, so it must have an interpretation that is of the form the change in y per unit change in x. So let's see if we can work with that. Take the expected value of y, given that x takes the value x plus 1, a 1 unit increase in x, and subtract off from it the expected value of y, given that x takes the value x. Well, that works out to be beta naught plus beta 1 times x plus 1 minus beta naught plus beta 1 times x. Do the arithmetic, and that works out to be beta 1. So, beta 1 is the expected change in the response per unit change in the regression variable. And that so it has a nice interpretation. It's not that different from the regular interpretation of a line, just now with the expected value, the conditional expected value of the response. Now remember, if we shift the x variable, it doesn't change the slope. We discussed that on the previous slide. What if we scale the regression variable? And we're usually scaling by a number, say a, that's positive. So what we can do is simply multiply and divide by a, and we can rewrite our regression equation as beta naught plus beta 1 tilde times x times a plus epsilon. So we've multiplied x by a, and our regression slope has now been divided by a. So in other words, multiplication of a regression variable by a factor a results in dividing the coefficient by a factor of a. Let me give you a simple example to hopefully solidify these points. Imagine this: if x is height measured in meters and y is weight measured in kilograms, a pretty simple regression problem, then beta 1 is interpreted in kilograms per meter. Converting x to centimeters implies multiplying x by 100 centimeters per meter. To get beta 1 in the right units, now we simply divide it by 100 centimeters per meter to get it back in the right scale. And here I just wrote a little equation to remind us. Also, I'd like to remind everyone that we can get a prediction for y by taking beta naught hat plus beta 1 hat and multiplying it by the x that we want to predict at. Now if we plug in the observed x's, then we get the fitted values, the ones who we're trying to make as close as possible to the observed data. But that doesn't mean that we can only predict at the fitted values. We can predict at any value of x we'd like to plug into the equation. However, we're going to have more reasonable predictions if the value of x that we plug in is in the cloud of data that we use to build the model. Later on, we'll also talk about how to account for that kind of uncertainty with prediction intervals. But for the time being, let's just talk about how we get a prediction. And in the next couple of slides, we'll go through an example of interpreting the intercept, interpreting the slope, and generating predictions from a specific regression modeling setting. All right, let's go through some code now to interpret our regression coefficients and show you running of the regression coefficients sort of in real time. The data set is the diamond data set from the Using R package. The data is diamond prices in Singapore dollars and diamond weight in carats, which is a standard measure of diamond mass. To get the data, you need to start out by using library Using R to get the Using R package and data diamond. And then I want to do ggplot2 because I'm going to do a ggplot first. So here, let me go through my ggplot commands. So I would like to assign to the variable g my ggplot. The data set is diamond. My aesthetic has the horizontal axis variable as carat and the y-axis variable as price. I'd like to get in the practice of labeling my axes. So my plot, I add a layer where the x lab is mass in carats and where the y lab is price in Singapore dollars. So let me run those lines, and then I'd like to add the points. I like to add the points with a black background and then a light alpha blended color on top. And then it's quite easy to add the regression line. So I'm going to add a layer that is geom_smooth, and method equals lm will add the regression line. And if you omit any arguments, it's just going to assume the regression line with y as the outcome and x as the predictor. And then I want my regression line color to be black. So let me run that line and then call my plot. There's my plot. You can see on my x-axis I have mass. On my y-axis I have price. And now what I'm plotting is the fitted line, the line that minimizes the sum of the squared vertical distances between these points and the lines. Now let's actually go through and get our fitted line. Just to remind us, the function lm is R's linear model procedure, so it includes regression as a special case. Y on the left-hand side of our tilde is the outcome, price, then tilde, think of that as sort of the equal sign in the model. Our x variable, caret, by default, LM includes an intercept. So if you don't want an intercept, you have to explicitly force it in the model. Then the comma, we want the data set that we're looking at to be the diamond data set. So in other words, we have to give it the data frame. Otherwise, it looks in the regular R environment for variables in the model. And we're going to assign that to the variable named fit. So let's see what that output looks like after we run it. So there I've run the model, and now I'm going to type fit just to see what it prints out. It basically just prints out the coefficients beta naught and beta 1. I would note that you can get a much more detailed printout by doing summary of the outputted variable from the LM fit, and you get this more elaborate printout. And we're going to go through in detail all of the numbers on this printout. You'll be able to interpret everything on this printout at some point after the class. But for the time being, let's just talk about the coefficients. If you just want to grab the coefficients as a vector, let's do coef fit. And there we get the intercept. It labels it as intercept. And the regression variable for the caret, the slope for the caret regression variable. So let's look at this 3,721 variable and try to interpret it. It's saying that we have an expected 3,721 Singapore dollar increase in price for every carat increase in mass of the diamond. The intercept, negative 259, is the expected price of a 0 carat diamond. So not very interesting because we're not interested in 0 carat diamonds. Now let's mean center our x variable so that the intercept is on a more interpretable scale. The first thing I'd like to do is assign it to a different variable, fit2, instead of fit, because I don't want to overwrite the original fit. LM is again my linear model procedure. My outcome stays the same, and now I want to mean center my predictor variable caret. So caret minus mean caret. If you want to do arithmetic operations inside equation statements in LM, you actually have to surround them by this I function. And then we still want our data set to be the diamond data set. So let's run that code. So I've run fit2, and there are my new coefficients. Notice, of course, the slope stays the same, 3,721, but my intercept has changed to 500. So $500, Singapore dollars, is the expected price for the average size diamond. In this case, the average diamond is about 0.2 carats. A 1 carat increase is actually kind of big. What about changing the units to 1/10 of a carat? We can do this just by dividing the coefficient by 10. So we know that we would expect to see a $372 increase in price for every 1/10 of a carat increase in the mass of the diamond. But let's actually show in R how this works as well. Here I am now assigning to the variable fit3 the linear model fit, where now instead of putting in carat, I'm putting in carat times 10. So the units of this new variable is 1/10 of a carat. The data is, of course, still the diamond data set. So let me run that, and then let me find the coefficient. And you get, of course, that is now 372 rather than 3,721. So imagine if someone came to you with 3 new diamonds that they had, 0.16 carats, 0.27 carats, and 0.34 carats. So here they are right here. And let me assign those. And they wanted to know what you would estimate the price would be. Well, you could do it manually by grabbing the 2 coefficients and multiplying the intercept, or adding the intercept plus the slope times these new values. Let's do that. And so you would predict 336, 745, and $1,006 for these 3 diamonds respectively based on your fitted linear regression model, which, by the way, from the scatter plot seems to fit pretty well. Often you don't want to do even that much coding. You want a more general method, especially when you get lots of regression variables. So there's this general method called predict that will take the output from several different kinds of model fits. Linear models are one example, but predict is a generic function in R, and it applies to several different prediction models. So we predict from the output of our LM fit, and then you need to give it some new data to predict that. So new data is a data frame that has the new values of x for the caret variable. Then when we do that, what you'll see is, of course, it gives you the same answer, though now in a way that scales up when we have lots of regressors in much more complicated settings. So you generally want to predict using the predict function. If you omit this new data statement, if you just do predict fit, I'll show it to you. It predicts at the observed x values, so it gives you the y hat values. If you want it at new x values, you have to give it this new data argument. I just wanted to briefly illustrate what the prediction was accomplishing. Here's our observed data points in blue. The fitted values, when we do the predict command, the fitted values in red, all of the observed x values and their associated fitted points on the line. These are if we were to draw vertical lines from the observed data points onto the fitted line, they would occur at these red points. When we predicted a new value of x, what we're doing is we're finding a point along this horizontal axis. That here I'm giving the 3 values that we want, 0.16, 0.27, and 0.34. We're drawing a line up to the fitted regression line and then over to dollars, and those are our predicted dollar amounts.